Hello, my name is Ioannis Mitlisagkas from UT Austin, and I will talk to you about fast PageRank approximations on graph engines. The problem of PageRank relates to ranking a bunch of nodes on a graph. So I want to find the important nodes on a graph. It originates in web ranking, and essentially the PageRank is a vector I'm looking for that maps every node to a number, and it's a distribution. So all of those numbers, with the importance of every vertex, they all sum to 1. The PageRank vector can be computed using eigendecomposition. Essentially, the first eigenvector of a specific modification of the adjacency algorithm, of the adjacency graph, is my PageRank vector. And the discrete interpretation people use often uses random walks to approximate the PageRank distribution. What we're looking for is an approximation of the top k mass. So what that means, presume I have a set of k vertices, okay? I will take those vertices, plug them into the true PageRank vector, and that will give me a number. That is the mass for that set of vertices, and I'm trying to maximize it. That is my objective. We're looking at graph engines because we want to be able to deal with this problem for large graphs, very large graphs. And specifically, we're looking into GraphLab. The idea is as follows. I want to run a graph algorithm on a very large graph. And the way to do that is I will write a vertex program. Basically, I will tell every vertex, when it wakes up, how to gather messages from its neighborhood, what kind of operations to perform, change in its state, and how to communicate back to its neighborhood its results. It's kind of like a message passing algorithm. Another important aspect of graph engines is how they deal with partitioning the graph. So what modern graph engines have converged to is essentially doing vertex splitting. So I have my original graph, I read it from the disk, and I will assign every edge I get to a specific machine on my cluster. That leads to the high-degree nodes being replicated a number of times. I will call one of them the master node, and the rest of them are called mirrors. So now the idea is that the master node will perform this computation here and change the common state for all of the vertices. But now the new state needs to be synchronized, communicated back to all the mirrors. And that requires a lot of network traffic. And that is the recognized bottleneck for this kind of application. And so the way we deal with that is we randomize the process of synchronization as follows. I'm given a parameter PS. So when it's time to synchronize the new state, I will flip a coin for every mirror. And if I get heads, I will draw a bridge. Otherwise, I will not communicate to that machine. So now my walkers need to either jump. Now my walkers can only use the bridges I drew. So my frogs jumping around my graph, they stop on B, and I tell them you can only jump to C or Z. That introduces dependencies between the random walks. And presumably I've broken the whole thing. We're not sure of its correctness at this point. But what we see in practice is what we saw eventually, both in theory and in practice, we get almost the correct answer. We get a very good approximation, and we do it very fast. So our contributions are a modification of the GraphLab engine, such that it supports this randomized synchronization primitive and an extension of its API. It's the implementation of this algorithm on top of the modified engine. And basically we see in the experiments that we get a 7 to 10 times faster operation. And in theory, we guarantee that the bias introduced is controlled. Thank you.